Okay, so experiment 4 is a simple experiment of how to do separations based on physical properties of elements and compounds. And some of that has to do with the classification of matter. And in Chapter 1, that very first assignment I gave you in Chapter 1, the very first video you guys watched, went through this classification process, right? And how we classify matter. So here's matter. How do we classify it? We put it as either a pure substance or a mixture. Okay? And the definition of a pure substance and a mixture can sometimes be a little confusing. So if you have something like carbon dioxide, water, versus oxygen, hydrogen, if I was going to classify those as pure substances or mixtures, what would I classify carbon dioxide as? Okay, so we would say that there's a carbon and oxygens. Is that a mixture? No, it's not. Do I have any mixtures on that list? I don't have any mixtures, right? They're all pure substances. So sodium chloride, it's a compound. It's a pure compound. It's table salt. You pull it out of your cupboard, it's a pure substance, right? If you put the sodium chloride in water, which is another pure substance, now it's a what? Now it's a mixture, right? So now I've created a mixture, and mixtures come in two categories. We have homogeneous mixtures, and we have heterogeneous mixtures. Homogeneous meaning the same. Homo, the prefix homo means the same. So homogeneous, therefore, a homogeneous mixture is one that's the same throughout the entire mixture. If I take a sample of salt in water, here's my salt water. Okay, I don't see any particles because they've all dissolved. They're completely dissolved. But if I take a sample right here at the bottom and a sample right here at the top, will there be any difference in the amount of salt that I find here as I find here? There won't be. It's going to be exactly the same. So that's why we say this is a homogeneous mixture, because it's the same throughout the entire mixture. Whereas a heterogeneous mixture would be one where if I take, let's say, salt and pepper, and I mix them, what's going to be the result? So let's say I have, this is my salt and pepper mixture here. Okay, can I guarantee that right here and right here are exactly the same composition of salt and pepper? No, it doesn't matter how much I mix that. I can't guarantee it. So that would be a heterogeneous mixture, a non-uniform mixture. So mixtures that mix themselves like salt and water, because think about it, you dump some salt in water, you let it sit overnight, the end result is the salt has dissolved. You didn't have to do anything, right? You could just let it sit there and it will dissolve. You can stir it. Stirring it adds energy, makes it dissolve faster, but you don't have to. You can just let it sit there and it will dissolve. So the particles dissolving themselves, they will do a perfect job. So if it becomes a solution, meaning one where the particles dissolve themselves and they separate throughout perfectly, solutions will be homogeneous mixtures. Okay? All right. So that's how we're going to classify homogeneous versus heterogeneous. Pure substances can be, like we said over here, either elements or compounds. So water is a pure substance. Oxygen is a pure substance. One's an element, one's a compound. But they're both pure substances. Okay? All right. So in this experiment, what we're going to do is you'll be first doing an investigation. So if somebody opens up to your report sheet there, the report sheet, you're first going to be investigating the properties of a few different substances. Okay? So we're going to have things like salt and carbon. Let me see. Let me look at the list. Okay, you're going to have, yeah. We're not going to be doing mercury, so you can cross that one off. Don't worry about mercury. We will have magnesium. Okay, we're going to look at iron, sulfur, magnesium. All right, we're going to determine some of the characteristics of those things and identify some of their physical properties. Okay. Then, if you turn over to part B, okay, you'll notice that you have 4 different substances: white sand, powdered carbon, powdered magnesium, and sodium chloride. These are 4 pure substances, and you're going to investigate what they do first in water, and then you're going to investigate what they do in 6 molar hydrochloric acid. Okay? So that should be a clue to you that you definitely need to have your lab coat, your goggles, all your protective equipment, because working with strong acids like hydrochloric acid, we don't mess around with that. Okay? So you need to be prepared. So you're going to take some white sand, you're going to put it into a test tube, right? So you have a test tube. You're going to put, one of the biggest mistakes people make is they put too much, okay? And water can only dissolve so much of a substance. So you take a little bit of water and you put a whole bunch of that substance. The little bit of water is not going to be able to dissolve all of the substance. And the question is, does this substance dissolve in water? And if you have way too much of it, you're not going to be able to answer that question correctly. Because what if it does, but you just had too much of it and you can't tell? Okay? So you really only need a very small amount of the substance. You put a little tiny bit of that substance in there, and then you put it in a, it doesn't have to be a large amount of water, but a significant enough amount of water that that substance should dissolve in it. Okay? So maybe like 2 milliliters. And that might even be what the protocol calls for. Let's see. Okay, so place a small amount of each of these substances into a separate 15 centimeter test tube. Sand, carbon, magnesium, and sodium chloride. Add 2 milliliters of tap water. Just DI water. Don't ever use tap water. Use the DI water, okay? We don't want to use tap water. Okay, and then it says, use plastic film to cover it. Parafilm will be fine. Okay, just use parafilm. You can cover it with parafilm. And then you'll mix it and see if that substance will dissolve. So that's the purpose of what we're doing. So you need you have your test tube. You put a small amount in, okay? And then you put 2 milliliters of water on it. And then you shake it after you put your parafilm over it. So you put your parafilm around it, so cover it with your parafilm. And you can shake it and see if it dissolves. If it is soluble in water, then on your report sheet, you will put a yes or a Y. Yes. Just put a Y. Y, it is soluble in water. N, no, it is insoluble in water. So just put a Y or an N on that report sheet for those. Okay? And that's what we'll be looking at. Now, the whole reason that we're doing that is because the next thing you're going to be doing is you're going to be given an unknown mixture. You're going to be given an unknown mixture of some substances. And your job is to identify what is present. Okay? So, let's say that the sand, and don't take anything I'm saying as true, okay, because we'll find out what's true tomorrow. But let's say the sand is water soluble, which obviously it's not because it would dissolve in the ocean, right? So sand is water soluble. Let's say it is. If it is water soluble, then if I have a mixture and sand is one of the components of that mixture, then I can separate the sand from all of the other things based on the fact that it is water soluble and the other things are not. Does that make sense? So I pour some water over it, and what's going to happen to the water soluble thing? It's going to dissolve, and it's going to come out with the water, right? It's going to come out with the water, and the other stuff is going to be left behind. And I have successfully separated those components. Okay? Now, the other thing we're testing is HCl solubility. Or I would rather say HCl reactivity. If it is reactive with HCl, then it will dissolve. If it is non-reactive with HCl, it will not. So you'll use a Y if it reacts with HCl. You'll use an N if it's not. Then when you're looking at your mixture, to determine if something is acid or HCl soluble, you would pour some acid over your mixture. If something in the mixture reacts and dissolves, then you can successfully separate it from all the other things that are non-reactive. Okay? And now you have separated another component. And then if there's a component that's neither water soluble or acid soluble, then that's the thing that's going to be left in the end in your mixture, right? So that's the process that you're going to be going through tomorrow to identify what is in the mixture. Okay? So up here above, they talk about things like filtration. So you're going to have a setup similar to this, where you're going to have a funnel. You're going to put a filter paper on that funnel. And I'll show you how to do that. Okay? You have it shows you actually right here. You have a round piece. You fold it in half, and then you fold it into a quarter. Okay, don't worry about tearing off the corner. Not a big deal. All right? And then you just prop it open. Okay? Through the middle. You prop it open and make a capture funnel filter, and then you can put that onto your funnel here, and you'll spray some water on it before you start, and that water will seal the filter to the funnel. Okay, so this is glass. This funnel is glass, and you spray the water on there, and it seals it. It makes it stick to there. Okay?
Inside the funnel.
What's that?
Inside the funnel.
It'll stick to the walls of the funnel. Yeah, inside of it. Okay, and then they use a stir rod, which is a wonderfully acceptable way to do it, but I'm not going to require you to use that tomorrow. You can just dump it straight into there if you so desire. Okay, and but you have to make sure it's seated or sealed to the funnel first. And then the other thing that you want to watch out for is not filling it above. So the funnel, or the filter, might only go to about right there. Okay? And if I dump so much of this that it goes all the way to here, then what can happen is it can get between the filter and the funnel, and it will run down through here without being filtered. Okay? And then you've just made a mess of your experiment. So you want to make sure that the level of your the thing you're filtering never gets above the filter itself. Okay? It's always below the top edge of the filter, so that you're ensuring that everything's being filtered. And then it's going to filter through here, and you're going to collect. So if the first thing you did was put this in water, you put your unknown solids into water, and you separate the water-soluble thing by putting it on here, the water-soluble thing is going to go through the filter with the water. What's going to stay here? The insoluble substances. The water-insoluble substances will be left on the filter. Okay? They will be left on the filter, and now I have, right here, I have separated a substance from here to here. Potentially I have. I can't see it because it's in water, but I'm assuming that if there was a water-soluble thing, I have separated it. Okay? Then I can take this and I can move it over this beaker. I can move it over here, and I can get another beaker, and then I can add some acid onto this filter. My solids are already on the filter, right? And then I dump some acid on there. You're actually just going to use a disposable pipette and squirt it on there, the acid. If something starts to react, what do you know? What do you know about the components that are in here? That there's an acid-soluble thing. Okay, and you go back to your chart earlier and you say, okay, what is the acid-soluble thing, potential thing in my mixture? Okay, and then that acid-soluble thing will run through and it'll run out into here. It'll leave the mixture, and you'll separate it into here. Okay, and then you can look at the things that are left over, which are neither water-soluble or acid-soluble. And then you can make a conclusion about all the components of that mixture. Okay? That's your job tomorrow. That's your job of what you're going to do to identify the components of the unknown. Okay? Based on your investigations earlier that you did. Okay? So in B part 2, observations upon evaporation of the water filter. What that's talking about is, if you go down a little farther, let's see, maybe up here a little. Right here, they're talking about this evaporation dish apparatus. Okay? So the water-soluble thing that you got, you can actually identify if there was something water-soluble by boiling away the water. Because otherwise, you won't even know if there was something there or not, because you won't see it dissolve and you won't see it when it's in the water. So to find out if you actually had a water-soluble thing, you have to verify that by evaporating the water. You put it in an evaporation dish like this. And the reason they put this watch glass over it is to keep it from sputtering out at the end. Okay? But once it boils away, all the water boils away, you would be left with that water-soluble component, okay, in the dish. It would be left. All right, so that's what this whole part is about, showing you the setup. We wouldn't really do this one. We would just do this one right here, okay? So we just do that rapid evaporation. The slow evaporation doesn't really work very well, especially for things that are in water, because this boiling water isn't going to heat this water high enough to really boil away the water very quickly. It's going to take days. Okay, so that would be inefficient. So we would want to do this. And then we'd be able to identify all those components. Okay, and then part C, conclusion. List the components present in the mixture. You will be graded on whether you were able to successfully list the components that were present in the mixture. Okay, so you're going to want to do your best to try to identify those. Okay, any questions about experiment 4? Okay.